All right. Hi, I'm George Mendoza from Baguio City, and this is the 14th episode of the Philippine Ruby Group podcast. Um, Today, I'm going to cover the code of the Ruby simulator uh, that was blogged on redbadger.com, understanding the Enigma machine with 30 lines of Ruby. So, did I say 13th episode or 14th? Because this is the 14th episode. But anyway, in the 13th episode, I tried to explain the Enigma machine based on the blog article. And on this episode, what I'll do is go through the simulator that was written there in that article. So let's get to it. Once again, if you haven't seen the 13th episode, I suggest that you go through it first before watching this one. Okay, let's go. I'll share my screen. Mhm. So there's our text editor, and here for a moment. Okay. Okay. I've made some changes to the code uh, to make it easier to trace the encryption and decryption that we'll see later. So I'll explain these changes later on. But for now, let's focus on the structure of the program. Uh, first, we first the program initializes the plug board, the rotors, and the reflectors, which are the three main parts of the machine. And then we have this big method called input that basically does the encryption and decryption of your string. At the last part of the program, there's an example test where we get the plain text, try to encrypt it using the input method, and then decrypt that same encrypted, that ciphertext, and compare the plain text with the decrypted value. So that's the whole program there. Within the input method, what happens is we iterate through each character in the string. This is our loop here. And in the first part of the loop, we try to rotate the three rotors like we do the hands on our clock. So if our rotor 1 is our second hand and our rotor 2 is our minute hand, rotor 3 is our hour hand, we rotate them independently, but we rotate the minute hand, our rotor 2, if the rotor 1 has done a complete rotation. Likewise, we rotate rotor 3 only if our rotor 2 has done a complete rotation. I should mention right now that I'm not sure about this divisor 25 for checking if the rotor has done a complete rotation. It's like if we're going to implement a clock, then I think the value here should be 60. In this case, since we have our rotor has 26 characters on it, 26 characters of the alphabet, and I think this should be 26. But I'm going to leave this as is for now. because it doesn't really affect much of the program itself. So now, once we rotate the rotors, we now try to get the encrypted version of each character from the string. So if you remember from the episode 13, we said that the machine essentially creates a circuit from the key that was pressed on the machine to the light bulb that lights up, which represents its encrypted version. Along the way, the circuit passes through your plug board, your rotors, then finally to your reflector, and then it goes back, passing through the rotors in reverse order, back to the plug board, wherein we finally get the character and the encrypted version of the character. So what this part of the code does is simulate that path starting from the key from your plain text up to the encrypted version that goes out back from the plug board. Okay. So just to recap, let's try this. Let's try running this program once before we try to trace through it. Okay. I can't find where. There it is. Okay, let me share my terminal. Here it is. If we try to run the Enigma Machine program, here it is. To recap, each row here is represents one circuit, one path from your plain text from the plain text of from each character in your plain text to its encrypted version. That's why if you check the first column, you can see the plain text. I have taken more, etc., etc. And then at the end, you have your encrypted version. These characters here represents the nodes on the circuit that form the path from your plain text to your encrypted version. And we'll see later how these nodes are computed or calculated by the machine. We'll also see at the bottom how the machine is able to get your your ciphertext. So RELL, that's the first column here, RELL, and decrypt it back to your plain text. So now your last column here is I have taken more, etc., etc. Okay. So far, so good. Let's dive into the code because it has some interesting Ruby idioms that you might encounter in your working with hashes and arrays. And it would be good if you're accustomed to them. We're going to use the program by bug to step through the program. Here we are. Okay, let me check if I'm sharing this. Last thing I want to happen is I'm not sharing the actual. Okay, So this is now our Enigma Machine Ruby program running under PhRUG. The first change I did is to seed the random number generator so that we get the same result every time. So move. In PhRUG, you'll notice there's a pointer here for the row that's currently executing, for the line that's currently executing. Okay. So this line 7, 8, and 9, we're going to set up the plug board. As you can see, this is one of the idioms I mentioned earlier. We're going to construct a hash using the square. I forgot the term for this. As I am just going to refer to it as square bracket method. So you can see here that we have a range from A to Z, your complete alphabet. We're turning it into a array and shuffling it, and then we're getting the first 20 characters of that array. But if you're not familiar with this idiom, you might be asking, okay, so we have an array, how does it turn into a hash? So let's say we have an array A, B, C, and D. So that's your array. If we pass it to a hash constructor, we splat it, and then we pass it to the hash constructor. What we get is a hash wherein your odd numbered elements are the keys, and your even numbered elements are the values. So basically that's what this hash, this square bracket operator does. So with our plug board, so in line 7, if we move next there, our plug board now is now a hash with 10 characters and basically 10 keys, wherein each key is assigned to another character, and where there's no character that's assigned to itself. The next part of the setup of the plug board is we invert the plug board and merge it into itself. What does inverting actually do? If we invert the plug board right now, what we get is this new hash, wherein your keys and values are reversed. So in here, in the original plug board, you have S pointing to N, and in your inverted plug board, you have N pointing to S. If we merge this inverted plug board back to itself, we now have a plug board where there's a symmetry. So your plug board now has 20 keys, and then where each key points to there's symmetry between the keys and the values. So if I get plug board S, I get N, and if I get plug board N, I get S. So as mentioned, we only have 20 characters right now on our plug board. What about the remaining 6? For those, we refer to line 9, wherein we call on the default proc of the plug board. What this default proc do is basically determine what will be the value for a key, for a hash given a certain key. And in this case, the value that's returned is the key itself. So for example, right now, if I get plugboard I get nil. But once we set up the default proc there, if I call plugboard I now, I get I. So this way, all the remaining 6 characters just point to themselves. Question is why? Honestly, I don't know. I think it simulates a hardware limitation with the Enigma machine. I'm not sure why there's that hardware limitation, but for now, let's just assume that there is. And this is why the plug board is configured this way. So we now have our plug board. The next step is we build the rotors 1, 2, and 3. So this is that line. We're doing parallel assignment. And for build the rotor, you can see the method here. Okay. We can see that we're again calling the hash constructor. But this time we have an array and we're zipping it with the same characters from A to Z, but this time shuffled. So what does this do? What does zip do? Let's try an example. Let's say we have this array and we zip it with another array. The result of zipping is it's like a zipper. You assign one item from the first array to the first item in the second array. And you create a 2-dimensional array as a result. So you have your A point, A and A1, B2, and C3. Okay, so far. Now we're going to pass this 2-dimensional array to our hash. And what that does is basically converts it to a hash. So now you have a hash where A points to 1 and so on. So that is what will happen with this rotor setup here. Run it now. What we'll have is 3 rotors, wherein the rotors, keys of the rotors are your alphabet in sorted order. Its values are same keys, the same characters in the alphabet, but in shuffled order. So that's the same for 1, 2, and 3. Now we're at the part of the reflector. And if you notice, if I go back to my text editor for the rotor, let me stop the, oops. Okay, I'm back. If I go to the rotor, to my text editor, okay. So this is the code for the rotor. You'll notice that it's similar to our plug board code. have your hash constructor. It's being created out of an array of characters. And then that hash is inverted and merged onto itself. The only difference between the reflector and the plug board is that in the reflector, you use all the characters from A to Z. Whereas in the plug board, you only assign the first 20. So for some reason, the reflector does not have the same limitation as the plug board. Why this is so, again, I don't have an idea why. But it's how the reflector is set up. Okay. So let's run that reflector code. Here. We're now on this line here. And we're going to move to next. Check the reflector right now. We have 26 characters. They're shuffled. But each key assigns to the keys, and the hash is the metric. So for example, P points to D, while D points to P, and so on. Okay. Now that we're done with the reflector, we can move on to the input method. But right now it's just declared. So I move next. And we're also going to declare the rotate rotor method. That also. Okay, now we're in the actual execution of the program. We create our plain text, and now we're going to try and to encrypt it using the input method. So here we step into input method, and we create duplicates of the rotors, 1, 2, and 3. Okay. What we want to do is to go through the loop, inside the loop here, wherein we iterate through the string. I'm going to break under line 24. And if I go next, I should stop there. Okay. So right now, we're iterating through the characters of the string. We're on the first character, I. Our index is 0. First thing we want to do is to rotate the rotors. Since our index is 0, all of the rotors will rotate. So I don't know if this is how the machine is supposed to work. I would think that probably you might want to rotate after doing the first encryption, but this is okay. How does the rotate rotor work? We step into the rotate rotor. We have another hash being created. So what rotate rotor does is first we get our rotor, we get its key and values, and then we return an array. That array has two values, the new key and the original value. What is the key that changes? If you ignore this condition for a moment and just focus on k.next, what this means is that we're getting the next character from the key. So if let's say if we have our letter B, if we get the next letter from that, we get C. So that's the reason why we have this condition here. If we're at the last, if our character is the last character, then we just change it back to A. Okay. Go up and check our rotor as it is right now. Check the original state of the rotor. If we move next, check the new state of the rotor. So if you'll notice on the top, our keys were initially A, B, C, and so on. And in the new state, we start with B, C, D. So in effect, we shifted the rotor one step. And we do the same for rotors 2 and 3. So that is how we're simulating the rotation of the rotors. Now we're on the part where we actually follow the path from our plain text to our encrypted text. We start with our character and we store it in our cars method, cars array. So this cars array I added to this program to make it easy to trace the path from the plain text to the encrypted text. And basically how we do it is we just pass on the character and check which character this your part of the machine is pointing to next. So in our plug board, for example, we have our letter I, and that I is pointing to I also. Because if you remember from earlier, this is one of the 6 characters that don't have that are assigned to themselves in the plug board. Move next, and now we check what character is I pointing to through the rotor, in the rotor. And that is K. So now our characters is IK, moves to the rotors. Now we have this path. We reach the reflector and go back through the rotors, but in reverse direction, from the 3rd rotor back to the 1st, until we reach the plug board, wherein we get the encrypted version. So now, if we check our characters, you have your plain text here on the left. This is the path it went through the plug board, through the rotors, through the reflector, then back to the rotors and to the plug board until we reach the encrypted version, which is R. And basically, we do that for the remainder of the characters on the string. If we, let's delete the breakpoints and go to the decrypt part, complete the entire cycle of the encryption. Next, that's it. Here, the encryption process. So you might be wondering again, that's great for the encryption, but how again exactly does the machine, or in this case, the simulator, how is it able to decrypt the encrypted version back to its plain text? In this case, what I'll just show is the okay. What we'll do is take the how we're going to do this. Let's go to the text editor. Okay. So the question is, how is a program able to use the same code, use the same structure, use the same hashes that are somehow random, but still able to get the decrypt, encrypt and decrypt the same text. The magic, I think, lies in the plug board and the reflector. First, these two are, as mentioned, they are symmetric. When you have, if you imagine the machine, you have their letters on the plug board, and those letters are plugged onto other characters. And because of that interconnection between two characters, that connection can work both ways. So if your A is plugged to B, then your current can go from A to B or B to A. So the plug board and the reflector are like this. They are symmetric. Another thing to remember is that the part here wherein after your current goes from the plug board through the rotors, when it reaches the reflector, it goes back in the other direction, but this time in reverse order. If we see this in practice, so we're back in the program and we're now going to decrypt the encrypted version. Okay. And we just check the first line. We compare the let's see if we can just copy paste it here. This is our first line. Please ignore the error. And this is the first line for decryption. Oops, sorry. And the D. Okay. So let me copy this and try to clean it up. Okay. So this is the encryption process, and this is the decryption process. If you remembered, all of this is implemented by just hashes. And if we try to figure out which connections are which, then we know that this is the plug board. This is the rotor 1, rotor 2, rotor 3. Okay. Magic of Sublime, we move everything one space apart. We now have our reflector. Oops. And then rotor 3, rotor 2, and rotor 1. Then finally our back to our board. And do the same for the description. Although it doesn't align properly. Okay. So if we compare the encryption and the decryption, in particular, we'll focus on the rotors because those are the ones that look kind of iffy. You think of the circuit again as a path connected by nodes from your source to your target, or your start and end of the path. And here, your I and K will be like an edge in that path. So you have an edge linking I to K. So that's the first rotor, and K to N, then N to J. Now think of it as when we're decrypting, we reach that same I at the end. In this case, we go through I, K, N, but in reverse order. This is because at the first state of the machine, the rotors are in the same position. And since, for example, if the connection between your reflector to your rotor, it's using it's like a bridge, wherein at one side you have in here you have your J node, and on the other side you have your N node. You have one bridge in the middle, but that bridge has 2 lanes going back and forth. And the keys, so that's the reason why at the starting state, your rotors, when going reverse order, will be the same as your rotors going through uh, its normal order. Again, the whole thing that makes things work are your plug boards and your reflector. Because the plug board and reflectors are symmetrical, in this case you have J pointing to R, which is the same as R pointing to J, and your plug boards, your D pointing to R and your R pointing to D. These symmetries allow the path to be traversed both from the starting point to the end point and from the end point back to the starting point. So that's pretty much it. Thank you very much for walking through with me through this walkthrough of the Ruby simulator of the Enigma machine. I hope you learned a lot of things with regard to idioms, hash idioms, and hash methods. If you have any questions, just you can post them on the Facebook page or on the YouTube page of this video. Hope to see you again next week at the same time. Oh, wait, I'm not sure if I'll be able to do this next week because I'll be visiting our office in the US. So the time zone might be messy. If there's someone who would like to volunteer for this podcast for the next 2 weeks, that would be awesome. Anyway, thank you very much. Hope to see you again. Have a good day.